Hello physics students. In this video, we're going to learn how to use Gauss's law to find the electric field of charge spread out in a planar fashion. So, Gauss's law, planar symmetry. I'm going to pause to give you a chance to jot this down, but I just want to point out this is a plus sigma. I like to draw it projected down on the surface, but it's plus sigma, the sigma symbol we've been using before for charge density. This is a box that goes above and below the plane, and this is A top, A bottom, A middle. So those are the things you might have difficulty seeing. All right, go ahead and jot this down, then I'll explain. Okay, so we're going to use Gauss's law, and just like in Gauss's law spheres and Gauss's law cylinders, we have to pick a shape that fits the geometry that will allow us to use Gauss's law to determine the electric field. Gauss's law, I could use a sphere here if I want, and Gauss's law is true, but it's not going to help me find the electric field. So what I realize is that I need a box with a flat top, flat bottom parallel to the plane. And the reason why is because I still need to know something about the distributed charge unit. I need to know that if I have a plane of charge and I pick a point over here, and then I imagine that I'm going to sum up the electric field from every little proton or small region of this plane, I realize that if I pick a point over here and a point over here, their horizontal components will cancel and the electric field will point directly away. Furthermore, if I go to the side, because this plane is infinite, no matter where I am, I'll have infinite amount of plane here, infinite amount of plane there, and so the electric field will be a constant at a particular altitude. Knowing that, I pick a box so it will sort of capitalize off that, those facts. So here's Gauss's law written out for this box. Now, the other thing is, once again, this electric field can come out and we just have E times area. But the only way that happens is if this plane is infinite. This is something that I actually forgot to mention when we were studying cylindrical symmetry. I found the electric field for an infinitely long line of charge, and I forgot to mention that I cannot use Gauss's law if the line is not infinite, if it's finite in length. Gauss's law is true even for a finite length bar or a finite length plane. But the problem is it just doesn't work to help us find the electric field. So I drew this diagram to show you why. This is a line of charge that is finite in length, and I basically calculated what the electric field would look like around that. Now, if you see that I make a Gaussian cylinder around, this is a cross-section of a cylinder, you can see that the electric field not only varies in length, but it's no longer perpendicular to the surface as I move along this surface. And so the electric field cannot come out of the integral in Gauss's law. I would have to, if I wanted to calculate the flux, I'd have to calculate this dot product, knowing this angle, and find the component electric field pointing outward, and then integrate over this. It would be a tremendously difficult problem to find the left side of Gauss's law. It would not just simplify to E times area. So that's why Gauss's law is true for finite length objects. The flux coming out of this cylinder is equal to Q enclosed over epsilon 0, but it doesn't work conveniently to allow us to find the electric field. And the same thing with this plane. The only reason this integral simplifies to this is because the plane goes infinitely in all directions, and therefore the electric field is a constant over the surfaces involved. But I want to just color coordinate this to show you more, so hopefully it gives you further understanding. So the electric field points away from this positive plane. It's not going to create flux along these side surfaces. It's only going to poke through the top of this box and the bottom of this box. So this is where the flux is in the portion of this diagram that's green. Probably doesn't show up that well next to the blue, but there and there. Okay, so that's the flux coming out of the top, flux coming out of the bottom, because the electric field points away from that plane. And so the left side of the integral becomes flux through top through bottom. The charge enclosed, if you look at this box here, it cuts away a portion of this plane. And the portion that it cuts away is right here. Okay? So that's where the charge is enclosed right there. And so, because this electric field is the same on top and bottom from symmetry arguments, we picked our box the same distance above and below, we can combine, and the areas are all the same, we could combine the left side to 2EA, and then this is just still sigma A over epsilon 0. The Gaussian area drops out, and we get the final electric field. So, go ahead and jot that down if you haven't already done so. Okay, now, what would happen if we had two parallel plates? One like this. We're going to study this later. That's called the parallel plate capacitor. You don't need to know that right now. But what you do is you have two plates. One you charge up positive, and the other one you charge up the same amount of coulombs negative. And, I kind of skipped ahead, but I forgot to mention that notice there's no z-coordinate here. This is a constant value. It doesn't change with altitude. If the plane is truly infinite, then the electric field is a constant all throughout. The other thing I forgot to do, sorry I'm kind of jumping around, but I forgot to do a unit check. Sigma is coulombs per meter squared. It's charge over area. And 1 over epsilon 0 gives our constant K. We have the correct units for electric field. All right, let's go back to this parallel plate problem. So we know the electric field caused by the positive is a constant pointing away from the positive plane, and it doesn't change with altitude. So I have these green arrows above this positive plane. The electric field points up, constant value. Below, it points away from the plane, so now it points down. The negative plane has electric field pointing towards it, so you see all the red arrows there indicating the electric field caused by the negative in all the various regions. You see outside these two parallel planes, the electric fields add to 0 from the positive and the negative. So there's no electric field above this arrangement or below. But in between, the two electric fields from the two plates add, because they're in the same direction. And so we have sigma over 2 epsilon 0 plus sigma over 2 epsilon 0, which just gives us sigma over epsilon 0. So that's the electric field inside two parallel plates. So I used the principle of superposition with the electric field value from one plate, but if I started from scratch, I could also calculate the electric field between these plates using Gauss's law. So I start with Gauss's law, the flux through my Gaussian box over here, and I make the box, it could straddle either the positive or the negative, it doesn't matter. But I made it go in, so this is like, I didn't draw it 3D, but this is basically the cross-section of a box that's cutting into this positive plane. So what you have to know is that the electric field out here is 0 in both these regions, so there's no flux through this bottom region, and the electric field in between goes upward. So there's no flux in the side surfaces because the electric field runs along the surface, but the electric field goes through the top here. So that's where we get flux, and I could color coordinate that by just sketching this in green. So that's where the flux goes through, nowhere else. And then the charge enclosed is right here, the portion of the positive that's been cut away from the rest of the positive. And so the charge there is the coulombs per meter squared times the meter squared, the charge density times area. And so that's the second line of Gauss's law. Now all I have to do is solve for the electric field. You see I could just cross out the areas. So If I haven't already done so, I'm going to create a pause to allow you to catch up. And finally, we have the electric field equaling sigma over epsilon 0 once again. Okay, so go ahead and jot that down. The next thing we're going to do is find the electric field in a slab. So what do I mean by a slab? I mean something that has thickness to it, like this board. Okay, so we want now the charge is spread in 3 dimensions, not just on the surface of a coulombs per meter squared. So we have a row, coulombs per meter cubed, all throughout this wood. The charge is spread out. Maybe in every cell of the wood structure, a biological cell, there's like an extra proton or something like that. And that would create a certain uniform row distributed. We want to find the electric field inside the wood and above or below. So inside or outside. Okay, so let me sketch that. Okay, so now what I'm going to do is I'm going to call the center of the slab z equals 0. And if the slab has a thickness d, whatever variable, you could use t maybe for thickness too, then this is z equals positive d over 2, and this is z equals negative d over 2. And we've got a certain, could be positive or negative charge spread throughout. So in order to find the electric field using Gauss's law, once again, I have to understand a little bit about the electric field from the distributed charge unit in order to be able to draw the right shape for our Gaussian surface. So here's what my thinking is. If I pick a point in the middle, right there, there will be a little bit of charge right here that creates an electric field dE like this. And another point down here that creates a dE going like this. A point over here creating a dE like this, and a point over here creating a dE like this. So for the middle, there are always 4 points, no matter where I pick them, that cancel each other. So I know the electric field is 0 in the middle just from my understanding of electric field in a distributed charge unit. However, if I move off this plane right here and go a little bit above, like here, now you can see that there's not as much positive charge above that point creating electric field downward. There's more charge below creating electric field upward. And so the electric field doesn't cancel completely if you're not on this plane. And in fact, the further you get to the surface, the bigger the electric field is going to get because we have more slab below than above, less to cancel, and eventually up here we've got all the slab below most electric field. So knowing that the electric field's 0 in the middle, but it grows as you go away from that midpoint, I've got to create a Gaussian surface that looks like this to find the electric field inside the slab. Okay? And hopefully why I picked that will become more apparent as I go through my calculations. So let's first begin with z is less than or equal to d over 2. In other words, we're inside the slab. That's what we're doing here. So we begin with Gauss's law. for that surface. Now, the flux, because of my reasoning, the electric field will point directly away from this central axis, so it will not go through and create flux through the sides of my box. It'll only create flux through the top of this box. So, here and here. So, the second line of Gauss's law becomes E times area, as always. This will be area on the top plus E bottom equals Q enclosed. Now, what's the charge enclosed? It's basically all the charge that's inside my Gaussian box. So it's this. Right there. So that'll be rho times volume. Before it was sigma times area. The coulombs per meter squared times the meter squared gave me the coulombs. Now it'll be the coulombs per meter cubed times the meter cubed. But what's the volume of our Gaussian box, that 3D shape that you see the two-dimensional cross-section of? What it will be is the area, okay, times how tall that box is. Now, if this is z equals 0, then this is z here. And so the box is actually 2z tall, right? From z equals 0 up, that's z, so this is 2z. So that's what we do, area times height. All over epsilon 0. Okay? So this left side becomes 2EA, and this side is 2 rho ZA over epsilon 0. So all I have to do is divide by 2, divide by area, and I get my final answer. Well, maybe I'll do the usual format. 1 over epsilon 0 rho z. So the formula shows what I reasoned out earlier, that at z equals 0, there's no electric field. We could see that. And then as z grows, the electric field grows as I go more and more to the edges of the slab. Also, unit check. 1 over epsilon 0 gives us our units of Coulomb, of K. Rho has units of coulombs per meter cubed. We multiply by the z coordinate, which is in meters, and we get kq over r squared units. So it appears as though we have the right form. Okay, the next calculation is outside the slab. So we could say for z greater than d over 2. Once again, I've got to be able to think of the correct kind of Gaussian shape. Planar symmetry is going to mean a box again. Okay, just a plain simple box. And this time, what I'll do, guess I haven't used this pinkish color yet. I'll make a Gaussian box that looks like this. Okay, so there's my Gaussian box. Again, I want to put this at the same coordinate below as above so that I don't have two different values of electric field. Like if this was like this, that would not be good. It would not give me the correct answer because I'd have two different E's and I couldn't solve for E. I have to make it symmetric about Z equals 0. So there's my shape. We start off with Gauss's law. For that Gaussian shape. Now, the flux, once again, the electric field is going to point away from the slab and away from the slab. So no flux through the sides because the electric field will run along those surfaces. It only pokes out of these two surfaces right here. So once again, I will color coordinate. The flux goes through this surface and that surface right there, the top and bottom of my box. So I could say again, E top times area top plus the electric field through the bottom times the area of the bottom that's going to equal Q enclosed over epsilon 0. Now, what's the charge enclosed? Well, if you look at this picture, there's no charge here. This is like air up here. The charge is only this part of the plane right here, or the slab. Right there, okay? So, we will take our coulombs per meter cubed and multiply by the meter cubed in there, in that region. That'll be the Gaussian area times the height of this part of this box here. And remember, the slab is thickness D, so this is D times area gives me the volume in there. Okay, well, just a little simplifying. These are the same electric fields because of the symmetry involved. So we could say 2EA equals rho dA over epsilon 0. Divide by 2, divide by the area goes away, and I get the electric field equals 1 over 2 epsilon 0 rho times D. Okay, so let me step aside, give you a chance to catch up with the notes if you need it. Okay, a couple points. This is, again, a constant electric field. So notice there's no Z coordinate. That means the electric field is the same right here, right above the slab, here, 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 all constant electric field. If this slab is truly infinite, that'll be true, okay? Or infinite enough for our dimensions involved. And then also the unit check. We've got our 1 over epsilon 0, K. Rho is in coulombs per meter cubed. And then the coordinate D, the thickness D is in meters. We have K coulombs over meters squared, as we should, okay? All right, before I move on to one final thing of the graph, I want to graph these functions. I just want to point out there is another option for Gaussian surfaces here. So we had to make these symmetric, as you can see, so that the electric field here and here were the same and we could solve for just one electric field. We could have also done this. Instead of drawing this as a Gaussian surface, we could have made a Gaussian surface like this. And the reason why is because when we put this surface, bottom surface along this Z equals 0, We know there'll be no flux in that bottom surface because there's no electric field along this bottom surface. So that basically takes this away. And then the volume of the box is only A times Z. And what you see if you do your Gaussian box that way is you get the same answer. Divide away the area, and you get right there, okay? So that's an option, either symmetric around Z equals 0, or one side at Z equals 0 and the other one up here. Same thing here. We could have made our Gaussian box like this. Well, let me just do this, okay? For the same reason, because now we had the symmetry, so these two electric fields were the same, but if we put the other surface here, there's no electric field at Z equals 0 from our distributed charge pre-analysis. So there's no flux through the bottom surface. So that means this term vanishes. And then, furthermore, now the volume where the charge is enclosed is not area times D, but area times D over 2. So we would have to add D over 2 here. And then when you solve, you get the same thing. So either that or symmetric works. Okay, last thing I want to do before I wrap up for today is I want to just sketch the graph as often we do with Gauss's law problems. We're expected to draw the graph that shows the pattern of the electric field around this particular charge distribution. So, yeah, usually we graph the electric field here. And now the z-axis is going to be tilted on the side a little bit, unfortunately, because we want an electric field to be in the y direction. So as we can see, inside the slab, the electric field grows linearly, starts at 0, and goes like this, and then reaches its peak value at d over 2, the end of the slab. And then from there, it's constant for all z, provided you don't go so far that the slab no longer looks infinite. And that peak value is right there. I'll write it as one fraction just to make it a little simpler. Okay. But the slab had also at z equals 0 in the middle. We can also have negative z coordinates. And there, the electric field, instead of pointing this way, will point the opposite way. So we'll say that's negative electric field for negative z values. And then at negative d over 2, we now are outside the slab. And once again, we achieve that constant electric field like this. And this will be negative rho d over 2 epsilon 0. So there's the graph. Okay, so I'll pause, give you a chance to copy that down. Okay, so just to recap, with planar symmetry, the Gaussian shape is no longer a sphere or a cylinder, it's a box. Okay, just like, you know, your Amazon box you get in the mail, right? Just everything's parallel, all the sides are parallel. The Q enclosed for the plane, in other words, like a sheet of charge, is sigma times area. Sigma being the coulombs per meter squared times the meters squared trapped in our Gaussian box. Gives you the coulombs, Q enclosed. For the slab, then the Q enclosed will be rho, the coulomb per meter cubed, times the volume, the meter cubed, gives you the coulomb inside. And on the left side, it's just E times area added together for the two surfaces where the flux goes through. So that's planar symmetry. I'll see you in the next physics video.